I typed 7 words into an AI. Write hello world in Python, and it gave me this in perfect syntax. Print hello world. That's it. One line, 22 characters. But what most people don't realize is that single line of Python triggers roughly 12,000 lines of code across 7 distinct layers of abstraction, millions of transistor state changes, and billions of electron movements. And every single one of those electrons, probabilistic. But we'll come back to that later. Let's go ahead and start at the top of this stack. Hello world. This is what you write. It's clean, it's readable. A child could understand what it's supposed to do after a few lessons, but Python doesn't run this. Your computer doesn't understand English or Python or anything resembling human language. So what actually happens? First, if you look at the top, Python reads your text and builds something called an abstract syntax tree. It's exactly what it sounds like. A tree structure representing the grammar of your code. Your one line becomes something like this. Every keyword, every function, every string actually gets a node. And Python is basically diagramming your sentence, the way you might have diagrammed sentences in grade school. Subject, verb, object. Except here, it's function, argument, and value. This tree is how Python understands structure, but it still can't actually run anything on your computer. Next, what Python does is it compiles all of your code into something called bytecode. These are simple instructions for Python's virtual machine. Load the function called print, load the string called hello world. Call the function with that string, 3 instructions, still abstract, still not running on your actual hardware. Bytecode is like sheet music. It tells you what notes to play, but it's not sound. Someone still has to perform it. And here's where things get interesting. Python itself is written in another language, C. When you run Python, you're actually running a C program that reads bytecode and executes it. So the call instruction, it triggers something like this in C. This is simplified. The actual implementation spans literally thousands of lines, but notice something. There's error handling in there. If call equals null. What happens if you try to call something that isn't a function? The code catches it, handles it gracefully. Every layer has error handling. Every layer has rules. This becomes very important later as we come to talk about AI in this giant stack. Now, the C compiler itself transforms that code into something called assembly language. You see, C can't actually fully compile that code to run it either. Assembly is a step away from the hardware itself. Each line maps almost directly to something the CPU can do. You'll see a lot of statements like push RBP means save the current base pointer. Move RBP. RSP means set the base pointer to the stack pointer. These are operations on registers, tiny pieces of memory inside the CPU itself. And finally, with all of that, we're actually getting close to the metal now, or at least closer to where everything's going on. And this is where we find a very interesting transition where assembly becomes machine code. Machine code is raw bytes, hexadecimal, and this is what the actual CPU, the brain of your computer, reads. The number 55 means push RBP. The bytes 4889E5 mean move RBP RSP. This is the bottom of the software stack, technically. We're actually not done here. There's something deeper than even this. Those bytes all get decoded by the CPU in something called microoperations at the hardware level. A single MOV instruction triggers a whole cascade. You have to fetch the instructions from memory, decode the opcode, calculate the effective address, read from the register file, write to memory, wait for the cache coherency, commit, and each of these involves transistors switching states, billions of transistors, and each transistor works by controlling the flow of electrons. Here's where things get philosophically interesting, or at least, in my opinion, they do. And before we go deeper, I kind of want to go backward, actually, back in time, to 1804. When we look into the kind of beginning stages of algorithms, we find ourselves in France, specifically a place in France where a man by the name Joseph Marie Jacquard was living in Lyon. He was a French weaver, and he invented something remarkable. It was a loom that could use punch cards to control which threads were raised and lowered, whole or no hole, up or down, binary logic. Before Jacquard, creating patterned fabric required a skilled weaver, an assistant called a drawboy, who manually raised threads according to the pattern. It was slow, expensive, and honestly limited in complexity. With punched cards, an unskilled worker could produce intricate patterns automatically. The same loom could produce unlimited designs just by changing cards. In 1839, someone used a Jacquard loom to weave a silk portrait of Jacquard himself. It required 24,000 cards, and each card had over 1,000 whole positions. Ada Lovelace, often called the first programmer, saw the connection immediately. She wrote that Charles Babbage's analytical engine, another pre-electrical era machine, weaves algebraic patterns just as the Jacquard loom weaves flowers and leaves. The punch card, whole or no hole, 1 or 0, this is where it all began. And here's the thing, those early looms had errors. Cards would tear, holes would be punched wrong, the silk would come out mangled, so they built systems to catch mistakes. They created standards for card sizes. They developed processes for verifying patterns before weaving, error handling at the very foundation. And you see, this is what brings us into the modern era, the reason I'm bringing into all of this. Every layer of our modern computing stack has the same story. In 1947, engineers at Harvard found a moth stuck in the relay of the Mark II computer. They taped it into the logbook with one note: first actual case of bug being found. The term debugging stuck. In 1994, a professor named Thomas Nicely discovered that Intel's Pentium processor sometimes gave wrong answers for division. The cause: 5 entries were missing from a lookup table in the chip's floating point unit. Just 5 values out of over 1,000. Intel had to recall processors. It cost them $475 million. At every layer, from punch card to silicon, humans have made mistakes. And at every layer, we've built systems to catch them, correct them, work around them. This is engineering. This is what we do. But let's go back to the beginning. Remember when I said electrons are probabilistic and then that was important? Here's something most people don't know. Your computer experiences random bit flips, not from software bugs, but from cosmic rays. High-energy particles from space collide with atoms in the atmosphere, creating showers of secondary particles. Some of those particles hit your RAM. When they do, they can flip a bit. A 0 becomes a 1. A 1 becomes a 0. In 2003, an electron in Schaerbeek, Belgium, gave one candidate exactly 4,096 extra votes. That's 2 to the 12th power, a perfect power of 2, the difference of exactly 1 flipped bit. A cosmic ray had altered the vote count. In 2013, a speedrunner playing Super Mario 64 watched Mario suddenly teleport through the floor. Analysis showed a single bit had flipped at memory address 0C5837800, changing Mario's vertical position, a cosmic ray in the middle of a video game. IBM estimated in 1996 that a desktop computer with 256 megabytes of RAM would experience about 1 cosmic ray bit flip per month. And now we reach the real foundation. Electrons are not little balls orbiting a nucleus. In fact, they're probability clouds, wave functions. You can never know exactly where an electron is. You can only know the probability of finding it in a particular location. This isn't uncertainty due to our instruments being imprecise. This is fundamental to reality. The electron generally does not have a definite position until measured. Transistors work by controlling the flow of these probabilistic particles. When you shrink transistors small enough, quantum tunneling becomes a problem. Electrons can tunnel through barriers they shouldn't be able to cross. purely due to their wave-like nature. The entire deterministic computing stack, everything from your Python code down to the machine instructions, is built on particles that are fundamentally, irreducibly probabilistic. So how does it work then? How do we make these things work so deterministically? We engineered our way around it. Transistors are designed with tolerances, and we use enough electrons that the statistical behavior becomes predictable. We build error-correcting memory, we implement checksums and parity bits, and we create redundancy. When a cosmic ray flips a bit in server RAM, ECC memory caches it and fixes it. You never know it happened. The entire history of computing is the history of taking something unreliable and making it reliable through architecture, through redundancy, through error handling. Hole or no hole in a punch card, moth in a relay, missing entries in lookup tables, cosmic rays flipping bits, electrons tunneling through barriers. Every layer uncertainty has engineering. Engineering, engineering. Which brings us back to where we started. I typed write hello world in Python into AI and it gave me code. People say AI is different. They say it's probabilistic, not deterministic. They say you can't trust it because it might give different answers to the same question. But think about what we just walked through. The punch card loom was deterministic, but the cards tore and the holes were punched wrong. Early computers were deterministic, but moths got stuck in relays. The Pentium was deterministic, but someone forgot 5 entries in a table. Your RAM is deterministic, but cosmic rays flip bits anyway. Electrons are fundamentally probabilistic, yet we engineered our way around that too. Every layer started with unreliability. Every layer becomes reliable through architecture. AI is no different. It's just the new layer. Right now, we're in the era of moths in relays. We're finding the errors. We're tapping them into logbooks. We're building systems to catch mistakes and verify outputs or just create redundancy. The criticism that AI is merely probabilistic misses the point entirely. The critics aren't thinking about the full stack. They're not seeing that everything beneath their feet is probabilistic too. We just did the engineering work already. When you type print hello, you're not just running one line of code. You're invoking decades of accumulated engineering. Thousands of people who solved thousands of problems, error handlers built on error handlers, all the way down to the quantum phone. Lovelace saw it. The loom weaves the patterns, the engine weaves the algebra, the computer weaves the logic. And now AI weaves the language. Same pattern, different layer. The only question is how long it takes us to build the architecture that makes it reliable. And based on history, I'm pretty sure we're going to figure it out. I mean, we always do. But that brings us all the way back to the beginning. That one line of Python, 22 characters, built on the shoulders of every engineer who ever taped a moth into a logbook. Stay curious, my friends, and until next time, goodbye.